In this video, we're going to answer questions and work example problems based on everything we learned in section 5 of chapter 2 about polygons. So convex, concave, and regular polygons, as well as polygrams. So let's get started. As the number of sides of a regular polygon increases, does each interior angle increase or decrease in measure? So we talked about a theorem that tells us the sum of the measures of the interior angles of any polygon, convex or concave, based on the number of sides of that polygon. Okay, the sum of the measures of the interior angles. Now, if you have a regular polygon, then we know that means that all the interior angles have the same measure. And since the number of interior angles of a polygon is the same as the number of sides, then what we can do is, to get the measure of the interior of each interior angle of a regular polygon, we can just divide this formula here by n. And you get this formula here that gives you the measure of each interior angle of a regular polygon based on the number of sides. So if we can write this, let's take this n minus 2 over n and put it out front here, so times 180. Okay, so since 180 is constant, we just need to analyze what this term does as n increases. Well, we can see that this is always going to be some ratio with the numerator being 2 less than the denominator. So okay, if we might have 3/5 if n is equal to 5. But then to exaggerate this, let's say the n was equal to 100, then the numerator would be 98. So as n increases, we can see that this ratio here is going to get closer and closer to 1. So it's going to be larger than the previous term with the smaller n. So as n increases, then, since 180 degrees is constant, as n increases, I is going to increase. So the answer here is increase. Okay, as the number of sides of a regular polygon increases, does each exterior angle increase or decrease in measure? Okay, so in regards to exterior angles, we talked about this corollary here that says that the sum of the measures of the exterior angles of a polygon, one at each vertex, is 360 degrees. Okay, so this was a little bit confusing because what we talked about is that I was wondering if this applied to just convex polygons and not concave polygons, but it actually applies to all polygons, convex and concave. But if you have a concave polygon, then there's no, you don't have to think about having one exterior angle at each vertex. So if you have a vertex that's associated with an interior angle that's not reflex, which, like all convex polygons, are going to have these types of vertexes, these types of interior angles, then you're going to have two exterior angles at that vertex that are going to be the same. They're going to be the same measure. But so like, okay, we can do, for example, here we've got two at these vertexes. There's two exterior angles at each of these vertexes. Right? You've got, here's one and here's another. Here's one, here's another. Here's one, here's another. Those are equal though, because they're vertical angles. Okay? But when it comes to but what is this in terms of a concave polygon? What's the exterior angle here? Well, there's not two of them in this case. This is just the exterior angle. There's no, with a reflex angle in a concave polygon, there's no side extensions. It's just this is the exterior angle and this is the interior angle. That's it. Okay. Now, but with a convex polygon, all of the vertexes are associated with non-reflex angles. So they've all got these side extensions with these two congruent exterior angles. This is the two exterior angles. This is the two exterior angles. This is not an exterior angle. The exterior angle needs to have one of the sides of the polygon associated with it. And so what this corollary is saying is that for any polygon, no matter what the polygon is, regular, concave, convex, non-regular, whatever, if you sum the measures of all of the exterior angles, but just taking one angle at a vertex like this, a convex vertex, just taking one of the angles, it's going to the sum is going to be 360 degrees in all cases, which is really interesting. Okay, and so with that, then, as the number of sides of a regular polygon increases, does each exterior angle increase or decrease in measure? Well, okay, a regular polygon is going to have, just like all the interior angles were equivalent in measure, so the exterior angle is going to be equivalent in measure. Okay, and so with if we can think about the sum of the measure of an exterior angle in a regular polygon, since even with a regular polygon, the sum is going to be 360 of all the exterior angles, no matter how many sides there are. But if there's going to be in exterior angles, the number of sides, then we can see as the number of sides increases, then the measure of each exterior angle of a regular polygon is going to decrease in measure. Okay, given that AB is parallel to DC and AD is parallel to BC and AE is parallel to FC, with the angle measures indicated, find X, Y, and Z. So we'll just go ahead and use everything we've learned up to this point when it comes to relationships between the angles of parallel lines and transversals and triangles, etc., and just see if our knowledge about polygons comes into play here. So perhaps this quadrilateral here or this exterior quadrilateral, we can use some of the information we've learned about angles and polygons to answer this question. But we can start by, okay, we can easily get this, right? So 77 plus 36, 113. Now 180 minus 113, you've got, so 67 degrees. Okay, and now from there we can easily get X, because X is going to be 180 minus 67, which we can see is going to be 113. Okay, now maybe can we use some quadrilateral angle relations here? I'm going to try and do that first before I dive into parallel lines and transversals, but yeah, I'm not seeing anything. So let's go ahead and analyze the parallel lines and transversals. So we can, let's see, extend this. Okay, so let's see. They told us that A, B, and DC are parallel, and A, D, and BC are parallel, and A, E, and FC are parallel. So, all right, we've got, let's see, we can do, looks like we have alternate interior angles here. So this is 77 degrees. And then we have alternate interior angles here. So this is 67 degrees. Okay. Now, here we've got interior angles on the same side of the transversal, which are going to be supplementary. So this is going to be 67 degrees. So Y is 67. Okay, now we can use the fact that the sum of the interior angles of a quadrilateral is going to be, so if we use this formula, that's going to be 4 minus 2 is 2. 2 times 180 is 360. So, okay, 67 times 2 is 134. 134 plus 113 is 247. So, okay, 360 minus 247 should be 113. Yeah. So 113 degrees. Okay. Now 180 minus 113 is 67. We could have also seen that these two are alternate interior angles. And let's see. We know that this, based on alternate interior angles, is 113. So does that allow us to get Z? No, not yet. Well, okay, we know we've got these two lines are parallel, and so we've got interior angles on the same side are going to be supplementary. So that tells us that 77 plus y plus z is equal to 180. So y plus z is equal to 180 minus 77 is 103, but y is equal to 67. So z is equal to 103 minus 67. So 36. So z is equal to 36 degrees. There we go. Okay, in pentagon ABCDE, with angles B, D, and E all being congruent to each other, so their measures are the same, find the measure of interior angle D. So B, D, and E are all congruent, but not necessarily A and C. So, okay, we can start with the sum of the measures of the interior angles of this is a pentagon, so N is equal to 5. So S is going to be equal to 5 minus 2 is 3 times 180 degrees. So 180 times 3, 8 times 3 is 24. So 540 degrees is the sum of the measures of all of these angles. So with that, we can say that if we say that this, since these are all the same, the measure is x. So if we have 93 plus 93 plus 3x, that's going to be equal to 540. There we go. So now let's just solve for x. So 93 times 2, 9 times 2 is 18, so 186. So 3x plus 186 is equal to 540. So 540 minus 186, so 3, okay. 354. So, okay. 354 divided by 3 is 118 degrees. That's the measure of angle D, E, and B. Okay, find the total number of diagonals for a polygon of n sides if n is equal to 5 and n is equal to 10. So, okay, we talked about a relationship that gives the number of diagonals of a polygon based on the number of sides. And we talked about where this comes from. So, okay, we've got D, the number of diagonals is equal to where n is the number of sides. Okay. So, all right, if n is equal to 5, then we've got, okay, so 5 times 2. So D is equal to 5. Okay, now if n is equal to 10, then we've got, so D is equal to 7 times 5 is 35 diagonals. Okay, find the total number of diagonals for a polygon of n sides if n is equal to 6 and n is equal to 8. So, same process. You've got n times n minus 3 over 2. So, 6 times 6 minus 3 divided by 2. So D, the number of diagonals, is equal to 3 times 3 is 9. Okay, in this case, you've got so 8 times 8 minus 3. Okay, so 5 times 4 is 20. Okay, find the sum of the measures of the interior angles of a polygon of n sides if... Okay, so they're not talking about a regular polygon here. This is any polygon, and we know that the sum of the measures of the interior angles for any polygon, concave, convex, whatever, with n sides is given by this formula here. Number of sides minus 2 times 180 degrees. And we talked about the proof of where this comes from, at least from the perspective of convex polygons. But this still applies to any convex or concave. So, okay, so if n is equal to 5, we've got 3 times 180 degrees. So 540 degrees. If n is equal to 10, we've got 8 times 180 degrees. So the sum of the measures of the interior angles of a polygon with 10 sides is 1,440 degrees. Okay, same problem, just different number of sides. So the sum of the measures of the interior angles is n minus 2 times 180. So we've got, in the case where n is equal to 6, 6 minus 2 is 4. So 180, 8 times 4 is 32, 720. So S is equal to 720 degrees. Okay, if n is equal to 8, then you've got 6 times 180 degrees. 8 times 6 is 48. So S is 1,080 degrees. Okay, find the measure of each interior angle of a regular polygon of n sides if these are the number of sides. So we know that since S is equal to n minus 2 times 180, that if you have a regular polygon, all of the interior angles are the same measure. But we know the number of interior angles is equal to the number of sides. So all you need to do is just to get the measure of the interior angles of a regular polygon, you just take this formula and divide it by n. And that's it. So, okay, if n is equal to 4, you've got 4 minus 2 is 2. Okay, so 180 divided by 2, because you get this. So you've got I is equal to 90 degrees. Each interior angle measures 90 degrees. Now, if n is equal to 12, you've got 10 times 180 over 12. So, let me get a calculator for this. 5 times 180 divided by 6 is 150 degrees. Okay, same question. So it's going to be n minus 2 times 180 over n. So we've got 6 minus 2 is 4. So we've got 360 divided by 3. That's going to be 120. Okay. Let's see. We've got, when n is equal to 10, you've got 8 times 180 over 10. 8 divided by 2 is 4. 10 divided by 2 is 5. So, let's see. 4 times 180. 144 degrees. Okay, Now, what is the measure of each exterior angle of a regular polygon of n sides? So the sum of the measures of the exterior angles of any polygon is 360, no matter how many sides. And so if you have a regular polygon, we know the exterior angles, at least one of the two, or they're all going to be the same measure. And if we have a regular polygon, we know that the exterior angles are all going to be the same measure. So all we need to do is the measures of each exterior angle of a regular polygon, since we've got n exterior angles, well, there's a pair at each vertex, but they're talking about the measure of each of just like one of those pairs. You just do 360 divided by the number of sides. So part A, we're going to have 90 degrees is going to be each exterior angle. And part B, we're going to have 360. So 12 times 3 is, so 30 degrees. Okay, same question. Here we've got 360 divided by 6. So we've got E is equal to 60 degrees. Okay, here so each exterior angle for this regular polygon is going to measure 36 degrees. Okay, here we're just using these same relations, but going in another direction. So if we know that the sum of the measures of the interior angles of a polygon is 900 degrees or 1,260 degrees, then how many sides does that polygon have? So what we need to do is we know we've got S is equal to n minus 2 times 180. Okay, so what we need to do is, we don't know n, but we know S in this case. So let's solve for n. We divide both sides by 180. Let's see, 900 is 5. So, okay, n minus 2 is equal to 5. So n is equal to 7. All right, part B, we've got, so n minus 2 times 180 is equal to, so n minus 2 is equal to 1,260 divided by 180 is 7. So adding 2 to both sides, we get 9. Okay, same question, just different sums of the interior angles. So n minus 2 times 180 is equal to 1,980. So n minus 2 is equal to 1,980 divided by 180 is 11. So n is equal to 13. Okay, part B, you've got n minus 2 times 180 is equal to 2,340 degrees. So n minus 2 is equal to, so 13, adding 2 to both sides, you get 15. Okay, what is the number of sides for a regular polygon whose measure of each interior angle is given here? So yeah, in this case, we know that the I is going to be n minus 2 times 180 divided by n. Okay, so that's the measure of each interior angle. So we just need to solve for n. So n minus 2 divided by n times 180 is equal to 108. So 108 divided by 180 is equal to 3/5. So we've got n minus 2 divided by n is equal to 3/5. So we can cross multiply. So you have 5n minus 10 is equal to 3n. Okay, subtracting 3n from both sides and adding 10 to both sides. So n is equal to 5. Okay, part B, we've got, so n minus 2 over n times 180 is equal to 144. So 144 divided by 180 is 4/5. So you have n minus 2 divided by n is equal to 4/5. So you've got 5n minus 10 is equal to 4n. Subtracting 4n from both sides and adding 10 to both sides, n is equal to 10. Okay, here we want to find the number of sides for a regular polygon whose exterior angles each measure what's given. So in this case, we've got the relation that the exterior angles of this regular polygon are going to be 360 divided by n, because they always sum to 360 no matter what, but they're all equal in this case, so you just divide by the number of angles, which is the number of sides. So we've got 360 for part A. 360 divided by n is equal to 24. So 24n is equal to 360. So n is equal to 15. Okay, part B, you have 360 divided by n is equal to 18. So 18n is equal to 360. So n is equal to 360 divided by 18 is 20. Okay, what is the measure of each interior angle of a stop sign? Well, okay, we've got 1, 2, 3, 4, 5, 6, 7, 8. So this is an octagon. And we know we could get the sum of the measures of the interior angles no matter what kind of octagon it was, even if it was concave or convex with all kind of different side lengths. But in this case, we can see this is a regular octagon. It's, it's just symmetrical everywhere. The side lengths are the same. So we know the interior angles are going to be the same measure. So with that, then, what we can do is we can use the relation of n minus 2 times 180 divided by n, the measure of each interior angle of a regular polygon. In this case, n is going to be equal to 8, because this is the sum of all the measures of all the interior angles. But since they're all equal, we just divide by the number of interior angles. So we've got 8 minus 2 times 180 divided by 8. So 6 times 180 divided by 8. 6 divided by 2 is 3. 8 divided by 2 is 4. So 180 divided by 4 is 45. So 45 times 3 is 135. So each interior angle in this stop sign is going to be 135 degrees. This is 135 degrees. Lug bolts are equally spaced about the wheel to form the equal angles shown in the figure. What is the measure of each of the equal obtuse angles? So what they're saying is that they're equally spaced with these equal angles. So we've got a regular polygon here. In this case, 1, 2, 3, 4, 5. That's a regular pentagon. So it's just the same as what we just did with the stop sign, but now we're going to have n be equal to 5 sides. So we have 3/5 times 180. So 3 times 108. Okay, with P being equal to the set of all polygons as the universe, draw a Venn diagram to represent the relationship between the given sets. So here we're given the set of all triangles and then the set of all isosceles triangles. Describe a subset relationship if one exists. Are the sets described disjoint or equivalent? Do the sets intersect? Okay, so we're going to have this universe here of the set of all polygons, P. Okay, so within this universe, in this case, we're looking at, so we've got this set of all triangles we can draw here, and this is, we can see because this entire set is within the entire set of polygons, this set T here is a subset of polygons. That's what subset means. It's contained completely within another set, but they're not equivalent sets. So like, yeah, if we had, it's not the exact, they're different sets, and just one is completely contained within the other. Then then in that case you have a subset. This is the set of all triangles is a subset of the set of all polygons. Okay, now where would isosceles triangles fit in here? Would it be over here, the set of all isosceles triangles? Well, no, every single isosceles triangle is a triangle, right? But not every triangle is an isosceles triangle, in the same way that every single triangle is a polygon, but not every polygon is a triangle. So isosceles triangles are going to be a subset of triangles. So here's the relationship. Okay. Same question, but we've got, they're giving us different sets. So let's draw the set of all polygons. Okay, now we've got right triangles. The set of all right triangles are going to be a subset of polygons. Okay, but now how does the set of all scalene triangles relate here? This is interesting. So we know that a scalene triangle is all about the side lengths of the triangle. It's if all three sides of the side, all three side lengths are not the same measure, then it's scalene. If two of the side lengths are the same measure, two to three, then it's isosceles. If all three are the same length, then it's equilateral. But a right triangle it has nothing to do with side lengths. A right triangle is all about if one of the angles of the triangle measures 90 degrees, then it's a right triangle. So we can, from that, we can automatically, the first thing we can think about is that, well, you could have a scalene triangle that isn't a right triangle. You know, I guess maybe one of those the same length. Let me try and exaggerate this. There's a scalene triangle. That's not a right triangle. Okay, and then, but in regards to right triangles, yeah, you could have a scalene right triangle. But you could also have an isosceles right triangle with the two side lengths being the same length. So what we can see is that, yes, there are going to be some right triangles that are scalene as well. But not all scalene triangles are going to be right triangles. But both of these are subsets of polygons. So they're both subsets, but their relationship between each other is that they intersect. They're not equivalent. They're not disjoint. There's no subsets here. It's just they intersect. Okay? Same question, just some different sets. So we've got this set of all the polygons. Okay, now we have acute triangles, which are all polygons. Now we have scalene triangles again. How do scalene triangles relate to acute triangles? Well, okay, here we've got a side length property and an angle property. So, all right, an acute triangle is a triangle to where all of the angles are within the triangle are acute angles. It's not obtuse, it's not right. Okay, you can absolutely have a non-scalene triangle be acute. Here's an equilateral triangle. That's acute. You could have an isosceles triangle. That's not scalene, but that's acute. Okay, we could definitely have an acute triangle be scalene. Something like that. So here we're going to have another intersecting relationship. yes, some acute triangles are going to be scalene, but not every acute triangle has to be scalene. Like these two triangles would be here. This triangle would be here. But then you have some triangles, like there's right triangles that are scalene would come here. Obtuse triangles that are scalene would come here. So these intersect within the set of all polygons. These two subsets, A and S, intersect within the set of all polygons. Okay. Let's see, the set of all polygons. Now we've got the set of quadrilaterals. So four-sided polygons. And how does this relate to equilateral polygons? So not equilateral quadrilaterals, equilateral polygons. Okay, well, these should intersect as well. Because you've got, okay, we can absolutely have equilateral polygons that are quadrilaterals, like a square or a shape like this. This is an equilateral polygon that's also a quadrilateral. That would fall here, right? But you can obviously have quadrilaterals that aren't equilateral, just a scalene triangle or whatever, okay? But then you could also have an equilateral polygon that's not a quadrilateral. So any regular polygon that's not four-sided, a pentagon, a regular pentagon, whatever, that would be in here. So these intersect within the set of all polygons. Okay, let's see. We've got the set of all polygons. Now let's see, how do hexagons relate to octagons? Well, okay, these are going to be disjoint. Disjoint means that they're completely separate. They don't intersect. Because no hexagon is an octagon and no octagon is a hexagon. It's two totally different categories of polygon, but they're both subsets of polygons. Okay, so here we've got the set of all polygons. Now, okay, we have triangles, but quadrilaterals, same thing. These are two different categories. They're disjoint. No triangle is a quadrilateral and no quadrilateral is a triangle, but they're both polygons. Okay, and now they didn't give an example of equivalent sets, but that would be the sets would overlap. The set of, it's like they're the same set. Well, you might say, well, how does that apply in practice? I mean, why would you think about the relationship between the set of triangles to the set of triangles? Well, no, it would come into play more with sets that aren't based on some definition or category. Like you can define sets to be whatever you want. It doesn't have to be some formal category or definition from a book. You could define a set to be a set of numbers, a set of whatever, and if it happens to be the case where, okay, you end up with two equivalent sets, then you say they're equivalent, and that just means that they're the same set. It's not an intersection, it's not a subset, it's not disjoint, they're the same set. A father wishes to make a baseball home plate for his son to use in practicing pitching. Find the size of each of the equal angles if the home plate is modeled as shown in A or as shown in B. Okay, so one thing we can do here is use what we know about the sums of the interior angles of any polygon, and that might be all we need in this case. But if we needed to go further than that, we could maybe separate this up into triangles and kind of analyze from there. But it looks like all we're going to need here is this. So we've got two pentagons here. So S is going to be equal to 5 minus 2 is 3, so 3 times 180. That's 540 degrees. Okay, so in part A, we've got, if we say that each of these are measure X and the other two are 90, so 90 plus 90 is 180 plus 3X is equal to 540. So 540 minus 180 is 360. So 120 degrees. Now in part B, we've got, if we say this is, let's just say y, okay, now we've got three 90-degree angles, so that's 270 plus 2x is equal to, it's still 540. So let's see, 540 minus 270. So 2x is equal to 270. So x is equal to 135 degrees. The adjacent interior and exterior angles of a polygon are supplementary, as indicated in the drawing, yes. Any exterior angle is going to be adjacent to the corresponding interior angle, and they're going to be supplementary. That's one of the ways you can see why they're congruent, why the two exterior angles are congruent. They're vertical, yes, but they're also both supplementary to the same angle. Assume that you know that the measure of each interior angle of a regular polygon is, yeah, that's the formula. Okay, express the measure of each exterior angle as the supplement of the interior angle. So, okay, they're saying that if we're dealing with a regular polygon, then we know in that case, if this is a regular polygon, then we know that the measure of angle 1 is, well, okay, we know all the interior angles are going to be the same, whatever the measure of angle 1 is, and the measure of all the exterior angles are going to be the same as well, whatever the measure of angle 2 is, because it's a regular polygon. So the measure of angle 1 is going to be, so we don't know what the polygon is, so we're just going to leave n as n. Okay, and so with that, then they want us to say that the measure of angle 2 is going to be equal to 180 minus n minus 2 over n times 180. Okay, so that's the measure of angle 2. It's a supplement of the exterior angle, or of the interior angle. Okay, now simplify the expression in part A to show that each exterior angle has a measure of 360 divided by n. So, okay, we can do, let's see, the measure of angle 2, we can factor out a 180 and get 1 minus n minus 2. And right, this is the measure of any exterior angle. They're all the same. So, okay, we can do n over n minus 2. Okay. Let's see. N minus 2 is what? N minus n plus 2, right? This is n minus n plus 2, so it's just plus 2 over n. So there you go. 180 times 2 is 360 divided by n.